Okay, so we are still on section 4.2. In our last class, uh, what we discuss is about null space and column space. So we learn if we are given a matrix, how to find the null space for the matrix and how to find the column space of the matrix. We learned that. And in today's lesson, it's just a continuation of the same section 4.2. So what we do is we will quickly look at the linear transformation again. It's just a quick revisit because we discussed linear transformation in chapter 1. But again, here we quickly do 1 or 2 problems just for fun. And after that, we will work on kernel. Okay, the next thing is we will look at the, we'll talk about the kernel, the concept of kernel. Anyway, so the first thing first. So recall the linear transformation. A linear transformation T from a vector space V into a vector space W is a rule that assigns to each vector X in V a unique vector T of X in W such that it satisfies these two conditions. T of U plus V equals T of U plus T of V for all UV in V. And for any scalar C and a vector U, then you have TCU equals CTU. Okay, so if the mapping or if the function or if the transformation satisfy these two conditions, we call it linear. So I believe example 6 type, we already did it in our last class, I think in chapter 1. I leave it to you and I trust that you'll be able to do it by yourself. So let us work on example 7 quickly. Okay, guys, you want this example 6 also done by me here? Okay, that's not a big deal. The question is T from R2 to R defined by this? Okay, so what is T of X equals X1 plus X2? This is given. Is it a linear transformation from T from R2 to R? Okay, let us check that. Now, first of all, let us consider, remember, the domain is R2. So let X, okay, the domain is R2 means it can be written as any objects in the domain is in R2, which can be written as, let's say, X1 and X2. And let's say another object is, let's say Y, which means Y1 and Y2. Okay, this one both belongs to R2. This belongs to R2. I consider the two objects. And then you know that X plus Y becomes X1 plus Y1, X2 plus Y2. I can write that. Now, according to this transformation, T of X equals T of X means, let me write X plus Y, because remember the two conditions, okay? T of U plus B should be equal to T of U and T of V. So X plus Y equals, let's see what happens. Our goal is to prove that this will be T of X plus T of Y. So T of X plus Y will be, X plus Y is X1 plus Y1, X2 plus Y2 equals, remember, any X that gives you X1 plus X2. Okay, X means here, so we can write this as, remember, X means, what this means is T of X means T of X1, X2 is given by X1 plus X2. What it does, this transformation does, is that this first coordinate and the second coordinate will be added. So in this case, so the first coordinate is x1 plus y1 and the second coordinate is x2 plus y2 will be added. That's the relation, that's the function, okay, according to this. So this can be written as x1 plus x2 and plus y1 plus y2. We can write that way. So this means clearly this one is actually t of x plus this is t of y, because t of x means t of x1 x2, which means x1 plus x2, and then t of y means t of y1 y2, which is y1 plus y2. Okay, so as you can see, condition 1 verify. So check 2 condition. So condition 1 checks. In the same way, condition 2 you can easily verify that let C be a scalar and x is x1 and x2 belongs to R. All we need to do, the second condition is T of Cu equals to, we need to prove that T of Cx equals, we need to prove that C T of x. That's all we need to prove. So let's check. So T of C, x means x1, x2 equals, you can write this as T Cx1, Cx2, you can write that way. Now the transformation is, the rule that the T has is, what T does is it actually changes into, you know, R2, the two-dimensional figure, into one-dimensional figure by adding these two components. So that's the relation, that's the transformation in this case. So Cx1 plus Cx2, which can be written as C common x1 plus x2. And this means we know that this x1 plus x2 is, we already know from the previous part, is that this is T of x. So checks the second condition. Since T satisfies both condition, T is linear. Okay, that's it. And I will do one more. Maybe let's look at example 8. T M 2 by 2 matrix to 2 by 2 matrix defined by this rule. Okay, the transformation is rule, it's a function. Okay, is this a linear transformation? Let us check that. I leave example 7 to you, and if you need help, then you can check my lecture note. I'll provide the detailed solution there. So now example what, 7 or 8? Example 8. The question is T, which is a transformation from M 2 by 2. Remember the matrix 2 by 2 sometimes written as this way, sometimes 2 and 2. They represent the same thing. So M 2 by 2 to M 2 by 2, and defined by, or such that, you can write, or you can say defined by T of A equals A plus I, where I is a unit matrix. Okay, I is unit matrix. So this is the rule. Now we need to check whether it is, it is linear or not. So again, in this case, what we do is we consider two vectors and one scalar, right? So let us consider, let A equals A1, A2, well, let's say A, B, C, D. A, B, C, D, let's say. A is this, and B another object in the domain, because domain is M2 by 2. I'm just considering one random general vector here, general matrix 2 by 2. Let's say this is E, F, G, and H. All right. Then A plus B will be, all of you know that this will be A plus E, and B plus F, and C plus Z, and D plus H. A plus B is, is given by that matrix. It is also 2 by 2. Now, all we need to do here is that, we'll check whether TA plus B equals TA plus TB, whether this is true or not. We want to check that. So let us calculate this. T of A plus B is T of A plus B will be A plus E, B plus F, C plus Z, and D plus H. Equals, what that T does is, you see, if there is A, then T is a rule, T is a function, and the output will be A plus I. So the output will be A plus E, B plus F, C plus Z, D plus H, plus I. I means 1, 0, 0, 1. Okay, that's what it does. Now let us calculate how much do you get. So this will be A plus E plus 1, B plus F, C plus Z, and D plus H plus 1. This is what we got. Now let us find what is T of A. Okay, I'm gonna erase this part right here. Okay, hopefully this space is enough for me. Okay, so let's check what is T of A. Is T of A means A, B, C, D. What this T does is, actually the output will be A, B, C, D plus I. I means 1, 0, 0, 1. And so you will get, this will be A plus 1, B, C, and this is D plus 1. All right, this is what you get. Now let's calculate T of B. T of B is E, F, G, H, which gives me E, F, G, H plus 1, 0, 0, 1. And this gives me E plus 1 and F, Z, and H plus 1. Now, and so if you add TA plus B, TA plus TB, what do you get? TA plus TB will be A plus 1, B, C, D plus 1, plus T of B is E plus 1, F, Z, and H plus 1. So if you add them, you're going to get A plus E plus 2, and then this will be B plus F, This is C plus Z, and this one is D plus H plus 2. Are they equal, guys? Please check whether they are equal or not. And clearly they are not equal, right? Because we have seen that this one right here is, that's what we got. So what we notice here is that T of A plus B is not equal to T of A plus T of B. So it actually failed the first condition, so you don't have to check the second condition, okay? So failed this condition. So T is not linear. All right, so remember, if you want to show that, there is another easier method for this one, you can just simply consider one counter example. All you need to do is you give a counter example and you'll be done. But but you can do this way too. Okay. All right, and let's move forward. Okay, guys, so the another concept, like I said earlier, that we'll be talking about is kernel. Okay, so what is kernel means? Here is the definition. I would like you to read this definition very carefully, okay? Let T from V to W be a linear transformation, then the kernel of T, written as ker T, is defined by all V in V. You see, V is the domain and the object V in B, such that T of V equal to 0. So it is actually the null space of T under T. Okay. Earlier in the previous section, we said that null space of A. So when we talk about the matrix, generally for matrix, it's null space of that matrix. And because the transformation was given by matrix, here transformation is given by T. It could be anything. And so if you put that input under T and the output is 0, then we call it kernel of T. Okay, the container that any object that you put under T gives you 0. And the range of T is defined by range of T equals all W, the range is this W here, W in W, such that W equals T of V. And notice that T can be written as matrix transformation. Sometimes T of X can be written as A of X. So in that case, kernel of T is actually null space of T, and range of T is column space of A. So they have this relationship. So T is a transformation. It could be anything. It could be matrix. It could be other kind of mapping. But when we say AX, we are talking about the matrix only. But anyway, so if you get it, great. If not, then with the example, with the following example, you will find, I think you'll find it more easy to understand the concept. Okay, let's look at this example. So we have T from R2 to R2 be defined by, so here is the transformation given. What this means is, the given transformation here is that T of X and Y equals X minus 3Y minus 2X plus 6Y. So this is the transformation given, okay? I'll write this way. So if you put XY under T, then the output will be this. That's all the transformation the rule given here by T. Both are in R2, remember. Now, we need to check if U is 3 and 1, is U be a kernel of T? So TU, is this U kernel of T? That means T of U is, you see, 3 and 1. U is 3 and 1. Now you plug in this here, that's the rule. So 3, x is 3, minus y is 1, and 2x is 3, plus 6y is 1. Now, if it is 0, then yes, it is in the kernel of U. If it is not 0, then it is not in the kernel of U. Let us check that. So that's going to give me 0, and oh, this is also 0. You see, yes, you got 0. That means yes, U belongs to kernel of T. In the same way, can you guys check part B and C by yourself quickly? So in part B, T of V, which means T of V is 0, 0. And so when I plug in this there, so I'm going to get 0 minus 3 times 0 and negative 2 times 0 plus 6 times 0, which is 0, 0. Yes, so yes, V is in the kernel of T. And part C, T of W means T of W is 1, 1. So that is 1, 1. And you guys are telling me that this is not equal to 0, 0. So this is not in the kernel of T. Okay. So this is, so no, W does not belong to kernel of T. And before, okay, let's do the last example, last questions from here, which is example 10. D is a transformation. D is a rule that gives us, that transform any element, any object from polynomial of degree 3 to polynomial of degree 2. And what is this D? D is differentiation, which means derivative. Okay, D is the derivative here, defined by D of P is P prime. So verify that D is a linear transformation. So we want to verify that the derivative is actually linear. So part A, how do we do that? Let us consider two objects and one is scalar. Okay, let us suppose that P, Q belongs to P3. Remember, P3 means it's polynomial of degree 3. This is polynomial of degree 3. So we consider two vectors from the domain, and let C be a scalar, which means C belongs to R. Then we need to verify, if we want to verify that D is linear, we need to verify two conditions. So we need to check two conditions. Condition 1, D of P plus Q equals, we need to prove that this means P plus Q prime. Remember, the transformation is this. Okay, this is prime, this is derivative. So you know from your calculus 1 that the derivative will be, if you have 2x square plus 3 derivative, if you have that derivative, then you can actually write 2x square derivative plus 3 derivative, which is 4x plus 0, right? So you can do that. So we already know from derivative that yes, derivative can be written as P prime plus Q prime. So this means basically this is D of P plus D of Q. So this first condition checks. Now let us check the second condition. So D of CP equals CP prime equals, we know from calculus 1 that if we have 2x squared, for example, derivative, what we can do is we can simply write 2 outside and then x squared derivative, which means 2 times 2x, so that's going to give you 4x. We already know that, we can do that. So I can write this constant c outside and I can write p prime, right? So this means c p prime is actually d of p. So this also checks. Yes, t is linear because it satisfies both conditions. So since d satisfies both conditions, d is linear. So this one is done. Now part B, describe the kernel of D. Okay, that is interesting. Describe kernel of D. Let me do it here. So in part B, describe the kernel of D. That means we need to find the kernel of D. That means an object in the domain, and that derivative will make that equal to 0. So we need to find that kind of objects here. I think from your calculus 1, you already know that derivative of constant is 0. Constant means the, something that belongs to R. You already know that, but let us, methodologically prove that, okay? Derivative of constant is 0, so you can tell me the answer right away, but let's do it, okay? So to find kernel of D, we need to find the set of all polynomials in P3 such that, because the domain is P3, remember, polynomial of degree 3. So any vector that you consider should come from P3 such that d prime of P equals P prime equal to 0. So that's all we need to find. So if, let us suppose one vector P in P3, okay, then what this means is P can be written as, it's of degree 3. So P is a polynomial of degree 3. So polynomial of degree 3 will be A0 plus A1t, A2t squared plus A3t3. Sorry. Or you can write x if you like. So I'm considering variable as t. Generally, we consider variable t, but if you want, you can write x as well, p of x, no problem. Okay, this is degree 3. So p prime, okay, the derivative p prime of t equals, that will be, this one will be 0, so you'll get a1t, sorry, a1. So find the derivative of that. Okay, if you find the derivative, you're going to get a1 plus 2a2 plus 3a3t squared equals 0. Okay, because we're talking about the kernel, or maybe I'll write equals 0 here. So then we can write p prime of t equals 0. We are trying to find the kernel. Kernel means it should be, derivative should be 0. The objects, when you find the derivative, will be 0, is actually the kernel of D. So we need to find that. So that means A1 plus 2A2 plus 3A3
I have a question.
T square. Okay, guys, this much now. I think you deserve a 10-minute break. So these vectors, like if you read the definition and if you read the theorem and if you understand it, then it's fun to actually work because everything is so logical. Okay, step one step after another step. It's so logical. It's really fun math. But if we don't understand, then this is very confusing. Just keep that in mind. All right, guys, 10-minute break, and we will see. I will see you again after 10 minutes. If you have any question, let me know.